So, chapter 15, we're going to be talking about exponential, logistic, and logarithmic functions. So we're just going to start with some basic definitions today. So an exponential function is something that we write as a times b to the x. But we have a couple of constraints here. We say that a cannot be 0. B cannot be, has to be greater than 0 and cannot equal 1. Why do we have these three constraints on a times b to the x? What would happen if a was allowed to be 0? The whole thing is 0. That's a constant function, not exponential. What would happen if we allowed b to be 0? Same thing, right? Like the whole thing just turns to 0. What would happen if we allowed b to be 1? Right, yeah, it just turns into a constant again because b to the 1 to the first is just, or 1 to any power is just 1. Maybe we should be careful and then say 1 to any finite power is 1. 1 to the infinity is indeterminate. We'll talk about that in AP Calculus next year if you take that class. Why do we disallow b being negative? That's the one that's a little bit trickier to see. Why don't we allow b to be a negative value? Grace? Right, that's what we've said, but why are we forcing it to be positive? Why couldn't b be a negative number? Right? Like we've defined it as the b's to be positive. But why do they need to be positive? Why are we making that? Why are we asking them always to be positive? Well, the exponent is the variable, right? So that can take on any value. So what would happen if x was, say, 1/2 and b was a negative number?
Oh, it's imaginary.
It would be imaginary, right? Because the 1/2 is the same thing as a square root. In fact, any exponent that is a fraction with an even denominator would cause the same thing. So you'd have like this function with infinitely many discontinuities in it, because there's infinitely many rational numbers on any like segment of the real line, which is like, that's some bad news right there. So that's the reason why we're not allowing negatives for b. Okay? So worth noting that all exponential functions have a horizontal asymptote, at least if they're defined as y equals a times b to the x. That horizontal asymptote would be at y equals 0. And let's just do a couple of simplifying checks to make sure that we can deal with these exponents appropriately. So let's say our f of x is -2 times 4 to the x. Can I write that as -8 to the x? No, why not? Well, remember, to multiply two numbers together, one of two things has to be true, right? If they have the same exponent, you can multiply the bases together and keep the exponent the same. Or if they have different exponents, but the base is the same, you can multiply them together by adding the exponents, right? In order to multiply two things together, one of those two things has to hold. If we look at this one, we have 2 to the first, or negative 2 to the first, and then 4 to the x. So those are distinctly different, both the bases and the exponents. So there's no multiplication that can happen here. Is everybody okay with that? Okay. So what am I going to get if I wanted to do f of 2? Well, that's going to be negative 2 times 4 squared. 4 squared is 16. Negative 2 times 16 would be negative 32. What if we did f of 0? What's 4 to the 0? 1. So again, remember that any non-zero number to the 0 power is equal to 1. 0 to the 0 is indeterminate. Again, we'll talk about what that means next year in AP Calculus, but it means it's could be lots of different answers, but it's unclear which one it should be. What if we have f of negative 3? So that's going to be negative 2 times 4 to the negative 3. How do I do a negative exponent? Anybody? Makes a reciprocal. So 4 to the third is 64. So negative 2 times 1 over 64 is negative 1 over 32. What else do we have? I have f of 1/2. So that means we have negative 2 times 4 to the 1/2. What is the 1/2 power the same as? Square root. So that's just going to be negative 4. So remember, a to the m over n is just going to be the nth root of a to the m. Just trying to remind us some of these exponent rules from last year that, you know, if it's been a little while, can drift on us a little bit. About f of negative 3/2. How am I going to do 4 to the negative 3/2, preferably without a calculator? Yeah, so what I would think about it as is I would separate out the parts of that exponent into 3 parts. So I think about the 1/2, the third, and then the negative, all separately. And as Rita had suggested, let's deal with the 1/2 power first because, well, taking the square root of 4 is easy. We know how to do that, right? So the 4 to the 1/2 is just 2. And then 2 to the third is 8. And then to the negative 1 is 1 over 8. And then times negative 2 is negative 1/4. So the key here is remembering that like the exponent of an exponent is multiplication. Everybody okay with this? Remembering these exponent rules, they're hopefully ones you still remember, but they're easy to kind of get turned around, and they're some of the most common mistakes I see students make kind of at this and then the upper levels. It's just not being quite solid enough on the exponent rules to get that stuff simplified the way you want it to. Let's take another example. This time I've given you some values for x and g of x, and we're asked to write the exponential function. So we're given a whole bunch of these points. I really only care about 2 of these points. Which 2 would be the 2 that I would want to use? What's going to make my life easiest? Yep, and yes. So from this one, if I plug this in, I get that 3 is equal to a times b to the 0. Well, b to the 0 is just 1. So I just get that a is 3. And then from this one, we can say 15 is equal to, since I know a is 3, times b to the 1st. So if I just divide both sides by 3, I get that b is 5. So our answer then is just going to be y equals 3 times 5 to the x. Note, I cannot call that 15 to the x. What do you guys think? That's pretty easy, right? If you have 0 or 1, makes life quite a bit easier. Mr. Gulick, what would I want to do if I didn't have 0 or 1 as a point? Well, let's do an example here. So again, we're told this needs to be an exponential function. And we're given some points. So what we have is an x and a y. If I plug those into my exponential function, I have an equation with 2 variables. But because I have 2 points, I can create a system of 2 equations with 2 variables. And that's a system I can solve. Now, hopefully from last year, remember 2 of the main ways we used to solve systems were substitution and elimination, right? Now, this case is going to be a little bit different because you notice instead of the variables being added, like we had when we solved systems of polynomials, here the variables are being multiplied. So when the variables were being added to do elimination, we subtracted the equations, right? Here, since the variables are being multiplied, what are we going to do with the equations? We're going to divide to do elimination. Great. So I'm going to divide one of these equations by the other. The choice you'd want to make to make your life as easy as possible is take the one with the biggest exponent and make that the numerator of the division problem. So that would be equation B, because -1 is bigger than -3. So I'm going to do equation B divided by equation A. So far, so good. So 12 over 48 reduces down to 1/4. A over A, well, that just reduces all together. And how do I do b to the -1 divided by b to the -3? Great. So you should remember that we subtract exponents. So -1 minus -3 is +2. We can then square root both sides. To get plus or minus a half. But remember, this is the b for an exponential. So what can we say about it? It must be positive. So we can just drop that plus or minus and just call it b is equal to 1/2. From there, we're going to substitute that back into either equation A or B. It doesn't matter. I'm going to choose to plug it back into equation A because, well, the exponent on the B is a little bit nicer than the other one. What is 1/2 to the -1? Oops, I meant that plugging into equation B, sorry. That was confusing, my apologies. What was 1/2 to the -1? Somebody started talking. 2, excellent. Just makes a reciprocal, right? So if I divide by 2, I get A is 6. So we'd say y equals 6 times 1/2 to the x. Everybody feel good so far? Okay. One of the things that we would like to be able to do with these exponential growth and decay problems, or exponential equations, is to be able to compare one to another, right? What makes them difficult to compare, though, is oftentimes they're written with different bases, right? This problem that we just looked at was a base 1/2. This problem we looked at was a base 5. Makes it really difficult to compare, like, you know, the rate in which one is growing versus the other when they're different bases. What we would like to do is be able to write them with the same base. The question becomes, okay, if I want to do that, what base would I want to use all the time, right? And the base that we use canonically is called the natural base. Oops, I swear I picked up black. Oftentimes referred to as Euler's number, which we abbreviate with the letter E. The way we find E is we took the limit as x approaches infinity of 1 plus 1 over x to the x, which evaluates out to be about 2.718, 2818, 28, yada, yada, yada. And that's a irrational number, so it's infinitely long. It never stops. Now, again, if you take calculus next year, we'll learn how to evaluate limits like this. But this is not trivial to do. What we would end up doing at this level is we would just kind of do this numerically. So what I would do is I'm just going to pick some values of x. So I'm going to go generate a big list of x's here. That's probably a lot enough of them, 322 x's. And then I'll just do 1 plus 1 over whatever that x value is to the power of that x value. And we'll just scroll that down. Excel is really good at this kind of stuff. And we'll make that a little bit wider or whatever. And if you look at the beginning, we started with the 2, then went to 2 1/4. We just keep scrolling, and we notice that, hey, eventually, like slowly but surely, like each one of these decimal places becomes like fixed And if you did this with enough decimal points for long enough, you'd get as many decimal points of accuracy as you wanted to. It would never come out to the irrational number because you can't do that numerically, but it gives you like enough to get a pretty good approximation. But certainly we can see this is slowing down, right? That it's getting closer and closer to some number. What that number is, I don't know. Well, I mean, we do know, but like we can't tell from that. Okay. And the weird thing about E is that Euler's number, that number E, like pops up in like some of the most unexpected places. So in particular, if you look at this is just the sum of two rational numbers to a power. And somehow that comes out to be an irrational number, which is really weird, right? Like you shouldn't be able to do operations to rational numbers and get an irrational, you wouldn't think. That's indeed what's happening. Weird, right? Okay. With this, we now have a new way that we can rewrite exponential functions. So we can write this as y equals a times e to the kx, where again, a can't be 0 and k can't be 0, but otherwise anything else goes. Again, we don't allow k to be 0 because that would make an exponent of 0, which makes e to the 0 1, which is just now a constant. But any other values of k are fine. And this allows us to write exponentials all with the same base if we choose to do that. We often don't, but if we wanted to, we could. So now that we have the two different ways that we can write exponential functions, we tend to classify our exponential functions as either growth or decay. And you have two types of exponential growth. You have unbounded. So that would look like this. And then you have bounded, which kind of looks like this. And again, like you have like an asymptote kind of going on here. For unbounded, if I have the equation y equals a times b to the x, the a is greater than 0 and the b is greater than 1. If it's the other version, a times e to the kx, here a is greater than 0 and k is greater than 0. If it's the bounded version, we have that a is less than 0 and b is between 0 and 1. You don't really need to write the 0 there. If you just write b less than 1, that's okay because the greater than 0 part is implied, but I'm going to write it there just so we don't forget. And then the same thing over here, a is less than 0 and k is less than 0. Next is decay. Again, we have two types of decay. We have bounded decay, which would look like, there's our bound. It's going to kind of go like that. And then we have unbounded, which again, if this is our asymptote or bound, it'd look kind of like that. So for bounded, that is a greater than 0 and b between 0 and 1. Or it's a greater than 0 and k less than 0. And then our last one is the only other possibility, right? We would have 4 choices. So this is a less than 0 and a between, or b between 0 and 1. And this one would be a less than 0, k greater than 0. Okay. Let's do an example story problem, just kind of working with an exponential situation. So it says, given that the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people. And assuming the population growth is exponential, in what year will the population reach 1 million? So if I read this, I know that I'm going to be writing an exponential equation, right? And eventually what I'm going to need to do is I'm going to need to solve that exponential equation when it's equal to 1 million, right? So the first step is to write that exponential equation. The second step will be to, once I have it, set it equal to 1 million to solve. So for step 1, if I look at this, the way I read it is the years, like my independent variable, that's my input. And the y, or the population, is like the y coordinate, the dependent variable. So I could do this as the 2 points. But if I do that, this becomes like that example 3 from a minute back, right? Where neither my coordinates start with a 0 or 1. What I'm going to do is define x as the years after 1990. By doing that, this first point turns into 0, 782,248. And the second point would turn into 10, 895,193. Now, there would be nothing wrong with doing it the other way, that we had written it in red, but by making that little adjustment there and calling x the years after 1990, I make the creating the equation part like a boatload easier. Because if that's 0, then a is automatically got to be the y coordinate. I've gotten the a for free. I haven't had to solve a system. There's nothing sneaky I need to do here. It's just like a little bit of plugging and chugging. So there's my y, there's my a, and there's my b to the 10th. So b then would be, I would divide both sides by the 782,248. And then we'll do the 10th root. And I'll drop the plus or minus again, since I know we're talking about the base of an exponential. We know that that number must be positive. So I'll pull out my calculator to do this. So there's two ways to get that 10th root. You can type in the number 10 and then press math. Go to option 5 that allows you to edit the root and make whatever root you want. So you can do it that way. So there's that. Or you could have written it as parenthesis 895 193 divided by 782 248, and then raise that whole thing to the 1/10th power. Either one is going to get you the same number. So either way of doing it in your calculator is fine. What I'm going to do, since I'm going to use this value later, is I'm going to store that value into a variable. Since it's a b, I'm going to just use the letter b. That way I don't have to worry about typing the decimal places and worry about like, oh, did I round too much or not enough? And like, if the b's are really close to 1 like this one is, it can be really sensitive to rounding. So I'm just going to store the whole thing so I can take the whole number with me. All right, so that's that. Now what I'm going to do to find or to solve the equation then, we want to solve 1 million is equal to 782 248 times the 10th root of 895 193 over 782 248 to the x. We're going to solve that for x. So last year, to solve an equation like this, what would we have to use? We have to use a logarithm. Have we talked about logarithms yet? No. So what I'm going to do is I'm going to just avoid using a logarithm right now. I acknowledge that you could do that. It would not be wrong to do that. And you're certainly welcome to do that in the homework. But we're going to do this just graphically, just to remind you of how to do that also. So what I'm going to do is I'm just going to do this graphically. I'm going to go ahead and type in my equation, 782 248 times, and then I'm going to use that value b that I stored to the x, and then number 1 million. Oh yeah, thank you. I actually think I just missed the 4. Right, that's just not enough digits. That's it, right? Okay, thank you. Appreciate the heads up before we got in there and like got the altogether wrong answer. Now, what I'm going to do is I'm going to graph these two things and look for the intersection. To do that, though, I have to be careful about my viewing window. So let's think about this. X is the year since 1990. So 0 is a good start because that's 1990. In 10 years, I went from 782 to 895. So almost from 800,000 to 900,000. By year 20, I'd expect to be right around 1 million. So maybe I'll do a little more than 20. Maybe I'll do 25 or 30 for my X. Now, the exponential growth is not going to be linear like it is that I've described there. It'll be faster than that. But like that's a good upper bound because it's quick and it's easy to do just by like estimating. And that's all I really want is something that's like reasonable. The Y's though, well, it starts at 782, right? That's my lowest population. And needs to get north of 1 million. So maybe I'll do like 700,000 to like 1.5 million. I think that's good. Go by 700,000 or I'll buy 100,000 or something. Let's hit graph and take a look. So this is my population function. There's my line for 1 million. There's my intersection. So I'm going to hit second trace, choose the intersect command. Because there's only 2 curves here, it doesn't really matter. I'm just going to press enter 3 times. And I get about 18.21 is my value for X. but that's, remember the X is years since 1990. So the question reads, though, that's not going to answer the question. It says, in what year will the population reach 1 million people? So this would be like between 2008 and 2009, right? During that year from 2008 to 2009. Now, if we're asked at the beginning of what year would the population be at least 1 million, we would say 2009, right? We have to round up, because if I plugged in 18, that would be less than 1 million. Plug in 19 and I'll be more than 1 million. So, all right. Okay, fair enough. So if I take this model then, and I do like, okay, let's say like, 200 years into the future, what should the population of our city be? Let's see, that is 11,608,838,830 or whatever. Like, absurd, right? That doesn't seem plausible. So one of the drawbacks with using an exponential function to model populations is it doesn't account for like a lot of reality when it comes to population, right? Like, there's only so much space that a city can occupy before it has to start building vertically, and then that's really expensive, and it means that like logistically you're gonna have to redesign your city with the intention of building it up. So like roads have to change, and like utilities have to change, and like power supplies and water and everything. It's an incredible undertaking to go from a city of like 700,000 to a city of like 10 million, right? Like that's a massive, massive change in like city construction. Not to mention like food supplies and like, birth and death rates and like diseases. And it's just like, oh boy, does not seem like a very realistic model to just assume the population can grow without any constraint to it. A better model would be something where when the population is small, it grows exponentially. But as the population gets bigger, that kind of levels off and starts slowing down, right? Where it reaches what we call a natural carrying capacity. There's some kind of population where, okay, once we kind of get up to this level, it's not really going to change from here because we've run out of space to grow or food, or there's too much disease, or what, like all these other limiting factors kind of work together to tamp the population down, so it really doesn't get above this amount. So the type of function that does a nice job of modeling that is called a logistic function. And again, you could model this either with a general exponential or with the with that. And I'm going to, okay, this is dumb. Okay, so one of the features of a logistic function is if we allow, or is that it has a pair of asymptotes. We have an asymptote at y equals 0, and we have a second asymptote at y equals c. This c is often called the carrying capacity or the limit to growth. I think I spelled capacity wrong. Shh. spelling is hard. A lot harder than this. Because the rules for spelling just don't make any sense. No. They're like really convoluted. These are coming from, English comes from like 8 different languages that have 8 different conventions for spelling. And just like, this doesn't, I hate it. Anyways. So we have this. Worth noting that that A, B, C, and K are all, for this to be growth, are all greater than 0, and B has to be less than 1. And decay is going to, again, A and C are greater than 0, and then B has to be greater than 1, and K has to be negative. So, for example, if I have some logistic growth function like this guy here, and we wanted to graph this, let's say we do. To graph this, I am certainly going to use the alpha y equals to get that fraction command in there, because this is a nightmare and a half to type in to get it to look the way you want it to, or to do what you want it to without that. Just makes it much, much easier to write it that way. And I'm just going to reset my window to something that's like less absurd. So I'll just go like a kind of a standardish window here. So there's the graph of my logistic. Notice it kind of looks like the letter S there a little bit. Sometimes these are called S curves for that reason. What would you notice here that this is growth or decay? If I look at the picture. Growth, because it's getting bigger as you move from left to right. That supports with B being less than 1. If I want the y-intercept, how would I get that? Well, that's just the place where the x-coordinate is 0, right? So 0.6 to the 0 is 1. 1 times 3 is 3. 1 plus 3 is 4. So that would be 0, 2.5. And the horizontal asymptotes are y equals 0 always. And the other would be y equals c, which is just the numerator. That's 10. That's it. Nothing really to do. We're just using facts here to do this, right? Very little math actually gets done. My last example, and we'll be done so for today, right on time, as we're rounding into 45 minutes of me talking right now. That's a little long, but not too bad. That's close enough for government work. All right. So here we're given a population model with a logistic growth. It says P is the population in the city T years after 1950. So T equals 0 corresponds to 1950. Like T equals 10 would be 1960. T equals 20 would be 1970, etc. Right? At the beginning of what year, beginning being the key word there, will the city have 1 million people? So again, what I'm asking to do is solve P of T equal to 1 million. Again, we could do this algebraically. You'd have to use a logarithm to do it. We haven't talked about logarithms yet. That's not my expectation. My expectation would be we just do it on the calculator graphically. Now, if you wanted to do it algebraically just because you're like, I'm in for the challenge, I think I can do it, that's cool. No big deal. You could certainly do that. It is well within your capability, although it's a little bit tricky for the logistic ones. But if you paid attention well last year, you should be able to handle that kind of thing. But I just typed it in exactly like it looked on my sheet of paper. And then I'll do 1 million there. Just like before, I'm going to do 0. I don't know how long this is going to be. I'm expecting maybe 100 years would be a decent upper bound on that. I don't really know. The y min, I'll go with 0 because I know that's a horizontal asymptote for this function. And the other horizontal asymptote is the c. Now I'm not going to type in that number exactly. I'm just going to do like 1.5 million because it feels like that's good enough. Everybody okay with that? So that's my setup. Let's go ahead and graph and take a look at what we get. Here's our logistic growth curve. There's our 1 million line. That's the intersection we're interested in. Hoo-ha, I got it the first try. Second trace, intersect command, enter, enter, enter. And I get x is a little more than 79, or I guess I said t in this case. 1651. So at the beginning of what year is this going to have 1 million people? Question is, should I round that up to 80 or down to 79? Up to 80. And then we add 1950 to this, so it would be 2030. Why did I round up? Because it says at the beginning of the year, at the beginning of 2029, you'd be 999,000 something. Be real close, but it's not a million. So even though it's like just like crummy little decimal points and everything, your instinct says round that down to 79, because that word beginning there is telling us to round up. Okay. That's about it. I think to this point you guys can do up to 16 from the problem set if you were so inclined. Now, if you have AP exams this week, I don't expect you to touch this until after, those are done and your test is done. But if you're interested in starting that, that's there available to you. If you have bigger fish to fry right now, I totally understand. Use the second 45 minutes of class to work on something that's a little bit higher priority to you right now. Or if it's just like, I just need to marshal my resources for a big mental effort this afternoon and just need to like sit and do nothing, I understand. Okay.